we're missing. Okay, here we go. Module 9B, Lab 21. Still talking about sound. Here we go. These are just some questions we have that we'll be trying to answer today during the lecture. Can humans hear the same sounds as dogs or other animals?
No. Yeah. Sometimes.
Well, yeah, that's the best answer. Sometimes, right, yeah. What happens to our ability to hear certain sound ranges as we age? We'll get to that. And what is supersonic sound? These are just a few things we're going to be looking at today. All right, our first blank we're going to fill in is supersonic speed. Any speed that is faster than the sound of the medium of interest. And what that means is, remember we talked about sound traveling through something. It has to travel through a medium, whether it's solid, liquid, or gas. And so depending on how fast it's going in that medium, if it travels faster than that, then it's called supersonic speed. Mostly we talk about the sound traveling through air. Okay, so and the sound, when we talk about the speed of sound, we typically are talking about it through air that we hear. Yes?
So whenever you make sound, it vibrates through the air.
Yes.
And gets to your ears. Okay.
Remember we showed that way the wave was moving like the slinky? Supersonic speeds create shock waves that produce a loud sonic boom. All right, we're going to talk about this guy. His name is Ernst Mach. He was an Austrian physicist, and it was interesting. He was studying some things and came across this idea of sound waves or shock waves. And what he did was he was actually experimenting with high-speed photography. And what he saw on a photograph was a bullet being shot. I believe it's through some thick liquid that is being shot through it. And he got a picture of the bullet passing through, and he noticed these waves coming off of it here. And he hypothesized that wave coming off there was being squished because of the speed of the bullet. That the bullet was going so fast that it moved through the medium, and that these waves right here were actually the sound of the bullet. Okay, and that what happens is when the bullet catches up to the sound that it made, it reaches what we know as a sonic boom. Okay, so because of his work in this, we call this sound of passing up the sound barrier Mach. We call that after him. Okay, so here's what we're going to see. We have an airplane. Not very many things go faster than the speed of sound. And I'm assuming you understand I mean speed of sound in air. And the speed of sound in air is approximately 776 miles per hour, about that, depending on the temperature, okay? The warmer the air, the faster will travel, the sound will travel. So here's our airplane. That's a jet, a supersonic airplane. That's why they call them that, because they can fly faster than the speed of sound. They can fly faster than 775 miles per hour. Most airplanes can do that, but laws keep them from doing that. We have legal reasons to keep planes from flying too fast. Mostly it has to do with it makes a very, very loud sound, and it scares people, and it rattles things and breaks things and knocks things off shelves and things like this. So we have asked pilots not to do that. Over the ocean they still do, so there's sonic booms going on over the ocean. All right, so the plane begins flying. It starts going very fast. It gets to the point where it's going 775 miles per hour, and it gets to what is known as Mach 1. Okay, so Mach is named after Ernst Mach. And then if it passes that up, it can go even faster than the speed of sound. Mach 2, Mach 3, Mach 4. I'm not sure how many Machs there are. Do you know? It might be 5.
My parents used to live by an Air Force base, and they had a couple windows broken.
Yeah, it'll break windows, and that's mostly the places where you were going to find a sonic boom is from military jets. Sometimes they still don't want them to make a sonic boom. They tell them don't do it over close by. But there are times when they are doing some sort of training, or there might be an emergency. Yeah. So and they'll make that sound. Did you have a comment, Erica?
Yeah. So how do they make the sonic boom?
Okay, I'm going to show you that. So what's happening is that the plane itself is making a noise. Yes, it's making a loud noise. We know this. We hear it when it flies overhead, right? And that noise that it's making is sending out those waves all around it. So right here, this engine of this airplane, here on the left picture, this engine's making noise, right? And it's sending that noise out in these ripples. That we see, yes? But when it starts to move, it compresses, it goes so fast, the plane goes so fast, that it catches up with its own noise that it's making. All right, so it catches up with its noise. Do you get it?
Mm-hmm.
So yeah, okay. So it's making the noise and it's moving and it's going so fast that the sound waves that it produces get compressed right here, so that the plane is going faster than the sound that it's making. And what that means is that the pilot will not hear the sound of his engine. The sound of his engine, which is in front of him, that sound will be behind him because he's going that fast. Okay, but people outside the airplane will hear it, and when it hits it, it's a very interesting phenomenon. So we call it a sonic boom. Supersonic speeds create shock waves that produce loud sonic booms, which is what your folks experienced with broken windows. A sonic boom is a thunder-like sound produced as a result of an object traveling at or above Mach 1, the speed of sound. Okay? If an object is traveling faster than the speed of sound, 775 miles per hour, that's an incomplete sentence. If an object is traveling faster than the speed of sound, what? It makes a sonic boom, I guess. I should have finished that sentence. Mach 1 is traveling just about the speed of sound. Mach 3 is 3 times the speed of sound. All right, I don't know if these were all blanks you were supposed to fill in? No? Okay, was this one a blank?
Yes.
Okay, yes.
So, in the study problems, they had like Mach 1.5 or something. They said it was 1.5 times speed of sound, but Mach 1 is the speed of sound. So shouldn't
Yeah.
it be 0.5 times the speed of sound? Too much.
Yeah, I don't know.
Instead of 1.5
I don't know that.
Where I hunt, there's a military base, and you can hear the jets. They're always flying, all the time. And so usually if you see an airplane, you hear it and you look
Oh,
where
I know
you
it.
see it, and they're like,
It's not
over
even,
there.
you notice that when you see a
You
plane
hear it?
flying, you're going, oh, I hear it right there, but it's like way over there. Yeah. Because our vision, we see the light traveling to our eyes is much faster than the sound traveling to us. That's the same thing with those kids with the experiment in the video last week. Yes, David?
How fast would a bullet be? Is it enough
Okay,
to cause
the bang that you hear from a bullet is breaking the speed of sound. Yes, so that bang you hear from a gunshot is a sonic boom. You know what else is when you crack a whip? That's a sonic boom. When a flag flaps, that's a sonic boom. Isn't that weird? When a balloon pops, that's a sonic boom. When thunder is definitely a sonic boom. Okay, because lightning is expanding the air around it, and the air moving causes that sound. You get it? So all these things are part of that deal.
They're just
Okay,
smaller.
so they're just smaller, yeah, but they're traveling that fast. Okay, they're traveling that fast. Okay, so here we go. So here's stopped, but engine running. Subsonic, see, he can still hear his sounds here in the second picture. Speed of sound, he can't hear the sound anymore, but the sound is still reverberating back here. Supersonic produces this boom. So supersonic is when the boom is produced. Now, when they're flying in the air, which is where planes fly, right, there's an interesting phenomenon that takes place when this happens. They break the sound barrier, they have a sonic boom, and it causes a condensation of all the moisture in the air around them, and it looks something like that. That's a visual of a plane going through a sonic boom. Okay, we're going to watch a couple of videos. One video is explaining sonic booms to us. The second one is showing us an actual plane flying. Okay, so let's start here. Monkey see.
monkey.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to answer the question, what is a sonic boom? A sonic boom is the noise produced by something moving through the air faster than the speed of sound. But how is a sonic boom produced? As an object moves through the air, it forces air molecules out of its way, creating waves. These waves move away from the object or propagate. If the object moves faster than these waves can propagate, the waves become more and more compressed. Eventually, they're unable to get out of the way of the moving object quickly enough and combine into one large shock wave that trails behind the object. Sonic booms come from the shock wave created by an object moving faster than its own sound waves. The shock wave forms a cone shape around the object, with the tip of the cone at the front and the base trailing behind. When you first see the object, it appears to be moving without making any noise. It's only when the base of the cone reaches your ears that you hear the boom. In order to create a sonic boom, an object must move faster than the speed of sound, about 700 miles per hour. Sometimes physicists call this speed Mach 1. Anything moving faster than Mach 1 is moving faster than the speed of sound. Any object that moves faster than Mach 1 makes a sonic boom. Although we usually associate airplanes and spacecraft with sonic booms, meteors and other objects entering the Earth's atmosphere from space make them too. A whip's crack is a mini sonic boom created when its tip moves faster than the speed of sound. Even nature makes sonic booms. Lightning makes air molecules move faster than the speed of sound and causes the sonic boom we call thunder.
And this is the actual, oops, let me go back. I have to click on this one. This is the actual plane. So it's going to be loud, so prepare yourselves. So they're out on over the ocean, so they're not causing any trouble. Watch it, there it goes. Now listen. You'll hear a second one. Oh, let's go back and do it again. Okay, notice that you're going to see the cloud first, right? And that's the boom, but we didn't hear it yet, and then you'll hear it. Right there. So that was, of course, a demonstration for those people there. All right. Temperature matters. Sound travels faster when the molecules are moving faster. If the air is cold, the gas molecules are not moving as fast, and the oscillations are slower than in warm air. So that's going to come into play when we do our little experiment right here. We're going to need to know the temperature of the room. Unfortunately, we have this thermostat right here that tells us it's 69 degrees in here. So we'll be able to use that. All right, so when we're talking about a sound intensity, how loud something is, we measure it in a something called bells. Okay, so that would be the when we're doing a math problem. This would, what do we call that when we have to have decibels? We call them bells or decibels. The bell is 1 bell equals 10 decibels, and that's important because most things we hear are going to be in the decibel range because of the way our ears hear things. There's a range here. There is a chart I'll be showing you of the sounds of different things. All right, the amplitude of the wave determines the volume of sounds, how loud it is. Remember we drew that wave thing like this last time, and the amplitude was how far up it went? Now keep in mind our sound wave is a different kind of wave, but we still have an amplitude in there. It's just harder to draw that. So we had you draw it there. But the amplitude is the how loud it is, and the volume is measured in bells. That says on the back cover of your textbook, you can compare the sound intensity of certain things. I will show you, I'll bring a chart up here in just a second. All right, so the Bell scale is used to measure the loudness of a sound. It's named after Alexander Graham Bell. You've heard of Alexander Graham Bell?
Yeah.
What did he invent? The telephone, right. The reason he was working with a telephone was he was working with transmitting sounds because his parents were deaf, and he was trying to figure out a way to let them hear things. And he ended up coming up with the telephone. It did not help his parents, but it did lead to, of course, one of those great inventions. He was a Scotsman. He was from Scotland, and he moved to Canada, and then he did a lot of his work in America, so we consider him an American inventor. Yes?
So, back then they used to have like a telephone line, but...
Not before Bell. They had a telegraph line that the Morse code went through, that kind of thing, right?
So how do they transmit the sound like through the air with a normal phone?
You're talking about the normal phone that he invented?
No.
Oh, you're talking about a wireless phone?
Yes.
Okay, so let me tell you how a regular phone works first. Okay, so the signal is taken through a wire, and then it goes through an amplifier that turns it back into, so it goes from, it's an electrical signal. So it goes from a sound wave to an electrical wave back to a sound wave using a special little transformer thing on there. So now when we're talking about our cell phones here, I've always been fascinated with the idea, I mean the telephone's one thing, but I was always fascinated, y'all don't even probably know what this is. Over the telephone line we used to send a picture, it was called a facsimile, a fax. And I used to be blown away by that. How do you take a picture, put it over a phone line, and it comes out a picture? I thought that was really strange. It's like a fax machine. We don't use fax machines as much anymore because so many things can be emailed now and texted and this kind of thing. All right, so the signal that's coming out of my phone is going and bouncing off of a tower, and the tower's amplifying it and sending it, and another phone is receiving that, and the phone is a computer that is translating that. Okay, so it gets kind of complicated, and Mr. Bell didn't invent that, the wireless part of it. In fact, it was Marconi who came very soon after this who, or actually right about the same time, Marconi was working with something he called the wireless, which was radio waves. So it was using some sort of wave to travel on. If you listen to a radio in your car, radio waves is what those are using. So the cell phone is using some sort of wave, some sort of electromagnetic wave, bouncing off the tower. The tower amplifies it. And I believe the towers are associated with a satellite. Is that correct? Yeah. And so they're functioning that way. All right, the Bell scale measures the intensity of a sound wave, which is determined by its amplitude. An increase of 1 bell is a 10-fold increase in intensity. So from 1 to 2, that's times 10. And back to the math questionnaire, Vis, on that one. I'll need to see those questions. I'll need to look at those questions more closely before I understand what they're saying. But it sounds like they're, like the way you said it sounded like maybe there was a problem with that math. But then again, it just may seem like it. You know what I'm saying?
One of the,
it was one of the speed of sound ones?
Yeah, for the on your own.
On your own. Okay. So keep in mind also this is a brand new book, and if there are mistakes, we're not surprised if there are mistakes. Okay. But a math question, I always have to maybe confer with the math teacher and figure out what the answer is on that one. We usually calculate in terms of decibels or tenths of bells because of the intensity scale. So we hear sounds between 0 and 130 decibels. The human ear can hear between 0 and 130. There's Mr. Bell. There's Alexander Graham Bell. All right, so that's how we show the unit decibels with a little d and a big B, because it's for a person. 1 decibel is equal to 0.1 bell. So we usually go in this round here. All right, so here's some sounds. Is this in your book?
Yes.
You're supposed to write these things down? Okay, so a soft whisper is at about 20 decibels. Conversation, about 40. I'm probably a little louder than 40 because I'm lecturing at y'all, so I'm yelling at you a little bit. Busy traffic, 70. Hey, be quiet. Busy traffic, 70. Pneumatic drill, I think that's a, you know, one of those kind of those kind of tools. A gas mower, somebody's mowing the lawn, you got 95. A rock concert, 115. Ear pain, 120.
Ear pain?
Ear damage, 130. Oh yeah, have you ever had something that's so loud that made you hurt your ears hurt? A sonic boom will do it. Oh, it hurts.
Oh.
You know, like little babies watching fireworks. They're like, you know, they want to cover their shooting guns. A lot of people wear ear protection to shoot guns because it hurts your ears.
Yes.
Wait, so if someone were to shoot you with a gun, you would not hear it because it's going faster than the speed of sound?
Okay, I see what you're saying. If I'm standing in front of it, no.
If you are the target.
If you're the target, yeah.
Well,
I don't know. There might be a delay in when you hear the sound. I don't know. I'd have to, yeah.
Well,
Ask your dad that question.
By your ear, it could just blow out your eardrum. You know?
I mean, you're going to eventually hear it, but if you're laying down on the ground because you've just been pierced by the bullet, and then you hear it, hey, that was a shot. What was that? Oh, now I know. Yeah.
Oh no.
So, yeah.
No. Bullet hole.
I believe it. Or maybe if the target was my backpack right here and I just happened to be standing next to it.
Yeah, that would probably do some damage to your ear.
Yeah, but just maybe not till after it struck. I think that's his point. When do I hear it? After it strikes me? So good question. Okay, so we wrote a couple of these things down in your chart. Okay. All right, so here's a math question. The sound from a typical vacuum cleaner is about 60 decibels, while the sound of a rifle firing is 140 decibels. How many times larger is the intensity of the waves coming from the rifle as compared to those coming from the vacuum cleaner? John, Mark, you have a question?
I think I know the answer.
Oh, you do? Okay. Well, so what we do here is we take what we know, which is 60, we put it over 1, and then we divide it by 0.1 bell to figure out, because we have it in decibels right there, so we have to figure out how many bells it is, because remember the bells, if we have the bells, we know it's a 10-time difference, right? Okay, so that's what we're getting for, so go ahead.
Oh, I believe you should subtract 60 from 140.
Well, first
get
we
80.
have to move our decimal point. We have to do that, so that's 6 bells right there. You see why we're doing that? Because we're not doing decibels, we're doing bells.
You can do that after.
Oh, okay, I see what you're saying. 140 would be 14.
And thus, you would get 8.
Okay, so then the rifle is 8 bells. You see where we got 8? 14 minus a 6 right there. The rifle is 8 bells louder than the vacuum cleaner. Since each unit represents a 10-fold increase in sound intensity, you have to multiply 10 by 10 8 times. So there's 10, so 1, 2, 3, 4, 5, 6, 7, 8. So that's 100 million. So the rifle sound is 100 million times louder than the vacuum cleaner. Wow. 100 million times louder.
I'm not surprised.
So if you had answered me 8, 8 wouldn't be the answer, right? 8 would be, it's 8 bells difference, that's the answer, but how much louder is the rifle? 100 million. You get it? So you may have a math question like that. There's probably some practice problems on your own, things like that in your book, so go ahead and do those math problems. They're not hard, just have to remember what we're asking for. If I ask you the difference of bells, then that would just be 8.
The OU problems?
I don't know. Let's see what this one says. This one says OIO 14.10. The sound from a power saw is 110 decibels. How many times larger than normal conversation at 40? So 40 is 4 because we're going from decibels to bells. Everybody understands that, yes? Okay. We're going 110 to makes to 11. So it's 7 different, so 7 zeros. So 1, 2, 3, 4, 5, 6, 7. So that's, if you just remember 7 zeros, right? Is that what we had last time?
8 zeros.
8 zeros? 1, 2, 3, 4,
10
5, 6, 7,
times
8?
10,
Yeah.
whatever the number is.
All right, nice. So just put your that many zeros on there. That's 10. What's that number?
10 million.
That's 10 million, right? 10 million. I'm looking at it going, is there 1,000? No. So the difference is 7, so 7 zeros, so 10 million. So the power saw is 10 million times louder. Crazy. Oh, here's study guide. It says study guide 18 and 19. Remember, next week we're going to have a quiz, and if you need to turn your study guide in, right? So apparently we're doing some of these. Highway noise on the phone, okay, 80 decibels. Traffic is 100 decibels. How much louder is the traffic? So that's a weird question.
100 times.
100 times louder.
Yeah, 100 times louder. Good. That was easy because it was just 2 zeros, right? Okay, an amplifier magnifies sound by a factor of 1,000. Okay, this is coming from a different direction. If a 30 decibel sound is fed into the amp, how many decibels will come out? So 3 bells were fed in. It's a 1,000 magnification of sound. So 3 more bells. That's 3 zeros from the 1,000. So a total of 6 bells or 60 decibels comes out. Yeah, you just follow the numbers there. Follow the zeros. So this is apparently study guide question 18 and 19.
Cool. Okay.
So if you want to take a picture of them, have 2 questions already answered there. Okay, good.
Already did it.
Already did it, done. No problem, right? No problem. All right.
Yeah.
Now, can we damage our ears from too much loud noise? The answer is absolutely yes.
Totally.
And y'all, young people, are in a bad place. Now, they had earphones when I was growing up, but not like you have now. The ones you can stick in here and have, noise canceling while it's stuck in here. You don't hear anything else except the music you're listening to, and you can kind of turn it up loud. And your little device will warn you when you start to turn the volume up, right? It'll say, listening at loud volumes might harm your ear. And you're like, shut up, and you keep going, right? So, yeah, we have to be careful.
It doesn't.
As we age, now I'm a grandma, right? So I'm much older than you are. And it turns out when you get older, higher pitched sounds are harder than here. Do you know this? Do you know that sound you have on your phone that goes really high and I wouldn't even hear it? And y'all would be going, oh, that's hurt my ear. I'd be going, what sound? What are you talking about? Because I can't hear it anymore. We're going to see why here in just a minute. Remember those little hairs in the ear? Okay, those little hairs in the ear get less and less responsive to sound, especially the ones at the high pitch area, apparently.
You would think it'd be the other way around.
That it'd be low pitch?
Lower pitch are quieter.
Yeah, but remember where they are in the cochlea? It happens wherever they are. Those tend to stiffen up more quickly, the ones that have the higher pitch areas. Usually that degree of hearing loss happens in the same in both ears. So it's, your whole hearing apparatus. You may feel like people are mumbling. Mumbler, speak up. What? My husband asks me what all the time now.
I have
What?
bad
What?
hearing.
Huh? And I have to yell at him.
What?
I have bad hearing.
It's harder to hear SH, S, TH, and F sounds. Words like shell, cell, and fell all sound the same. I don't have that problem. I can tell the difference in those right now. So I'm thinking when all those sound the same, maybe it's time to retire and just be a grandma, right? All right, here we go. So here's the ear. This is actually specifically a condition called tinnitus or tinnitus. Have you ever heard anybody who said they have a ringing in their ears? And there's no noise, and they hear a ringing? My husband does have that, and so that's why I think it's hard for him to hear sometimes, because he's got this loud clanging in his ears. It has to do with those little hairs, the ones inside the cochlea, and notice how they're damaged here. They're completely gone, right? They've been shaved off or otherwise atrophied. So atrophy is a process of just kind of getting really thin from not being used properly. It just has to do with age and damage due to putting too much sound in your ears. So you know, a lot of rock and roll stars, like the big time rock and roll stars, are like 75 and 80 years old right now. They're old men, and they're still playing rock and roll music, and they all have hearing problems. All of them do, because they've been listening to loud music. I went to a concert recently in Houston, and you know, we're inside this building, and boy, I mean, it was so loud, my ears were ringing when I came out. And you can imagine the person on the stage making the sounds, right? That he's got to be around that sound every night when he's got this concert going on. It's going to cause, and he's an old guy, so he's going to have damage to his hearing. And it all has to do with those little, the way that the hairs are moving. They get less and less fluid. They get kind of stiff. The hairs get kind of stiff. All right. Wavelength and sound. Okay, the shorter the wavelength, the higher the frequency. Now, I will confess to you here that I sometimes get wavelength and frequency mixed up, the words. And so I'll say frequency when I mean wavelength and vice versa. Okay, so I get those mixed up, yes?
There's nowhere for us to put this.
Nowhere to put this, okay. So just know this, if the wavelength is shorter, the frequency is higher, which you should remember from our,
It was in our last week.
was that from last time?
Yeah,
Did we
filled it
fill
in.
in a blank? Oops, there's a book here. Remember when we were doing our,
Tuning forks.
I'm having a bad day. Yeah, tuning forks. And
Ooh, we get to
the,
play with them again.
yeah, the little one has a higher
Do you
sound
hear that?
than the, can you hear it?
You hear that?
That's a lower sound,
Yeah.
right? Because it's got the,
It's longer.
it's longer, right. So let me fix my little pointer that just fell apart over here.
Is this shorter and higher than longer and smaller? Why isn't it saying shorter, longer, or longer, higher? Shorter. Instead of higher and smaller.
The longer the wavelength, the smaller the frequency. The longer the wavelength, the smaller the frequency. Oh yeah, why does it says that? It does say that. That's
If
kind of
you use
annoying.
like smaller and
Yeah, smaller and
larger.
higher. So smaller, I just need you to know smaller and higher are the same thing.
higher and lower.
Yeah. Smaller and higher are the same thing. We hear the higher. The smaller we would see if we could see it, right? Okay. Is this gonna work? Yes, yeah. Okay, so there is our wave. Remember, it's a longitudinal wave.
Scissors?
That is a tuning fork.
But they
And somebody mentioned last time on the big one especially how we could see it. You could actually see the vibrations. You can actually
Yeah,
see it,
I can see it.
right?
You can see it buzzing.
It's going back and forth. Because it's big enough, I can see it and it's producing a wave like that. Okay, wavelength and sound. They are inversely proportional. Is this one a blank you have to fill in?
Yes.
Okay, so wavelength and frequency are inversely proportional. Pitch is an indication of how high or low a sound is. So pitch is another way of saying high, right? High pitch, low pitch, right? High, low. And it's primarily determined by the frequency of the sound wave. So I'm trying to remember now. These tuning forks, the number printed on there is the wavelength or the frequency. I get it mixed up every time. When the frequency is low, the pitch you hear is low. So maybe that's talking about, that's frequency right there. This number that's listed on this big one is 256. So it has a low frequency. Yeah, 256, low frequency, and this little one is a 512.
Oh, that's high.
Do you hear that?
I hear that.
Alright.
Can you hear it?
I can.
I'm not very close to you, that's probably wrong. Okay, going to help us understand a little better. Watch. Okay. Once again, we're going to show the waves in the not the longitudinal wave, but the transverse wave, because it's easier to understand it that way. Okay, that's the only reason we're showing it in transverse wave. Yes.
Why did they call the monkey wrench the monkey wrench?
I don't know. Do you know?
I don't know.
I don't know either.
I'm
That's a
really
very good
curious.
question.
Is that a monkey? Oh, that's a monkey wrench on the video. Okay.
Yeah.
Here we go. Let's just listen to what this guy says.
Because it's made for
Welcome back. Once again, we're going to use our PhET simulation to look at the relationship between frequency and wavelength and see if frequency and wavelength affect the velocity of the wave at
He's
all.
from Canada.
You might be surprised by some of the results.
That's it.
First of all, we'll start by oscillating the end. Again, we're creating a transverse wave. We can see that the disturbance is perpendicular to the direction the wave is traveling. And once again, we'll turn off the damping. So we don't want any friction to be occurring. We want a nice clean wave that we can study easily, that's traveling through a window. Again, we choose the window so that it does not reflect and come back on itself. We just want to look at the effects that frequency has on wavelength. So up top you see a slider that gives us our controls over frequency. I can turn it to low frequency or high frequency. You can ignore the number. The number 50 does not mean 50 hertz. 50 hertz would mean that the wave is being created 50 times per second, and clearly that's not true. In this simulation, the 50 just represents the fact that it's at 50% capacity. That would be 100% capacity up at this.
Technicalities, don't even worry about
So we can adjust the frequency of the oscillations by moving that slider.
that.
So let's start with a low frequency wave.
Okay.
And we can see right away when I create a nice low frequency wave, very few waves per second, the wavelength is quite long. And if I create a higher frequency wave, more waves per second, it in turn creates shorter waves. The wavelength gets smaller. Now, if I choose a frequency of, let's pick 20. Okay, so there's a frequency of 20, and I'm going to pause it. I'll step it through so we see one full wave, 2 crests. Now I'll grab a ruler, and with a frequency of 20, from crest to crest is one wavelength, and we can see that it's roughly 80 centimeters. From here to here is roughly 80 centimeters. Now let's take our frequency and double it. Let's bring it up to 40 and see what happens. Okay, so I've doubled the frequency. And again, I'll pause it and measure from crest to crest.
Look at that.
And we can see
It's half.
that our wavelength is now 40. So doubling the frequency has halved the wavelength. Seems to be an inverse relation that's occurring there. Now, if I double the frequency and half the wavelength, since velocity is frequency times wavelength, the effect of one is being countered by an inverse effect on the other variable. So in other words, doubling f means halving the lambda, the wavelength. So that would make the velocity constant. We can see from this sim that this is in fact the case. If I run the sim at a fairly high frequency, so let's bring it up to 80, we're making many waves per second, and then suddenly slow it down. Here, I'll speed it up again, and slow it down, speed it up, slow it down. Notice that the speed at which those crests are traveling does not change. If it did change, these higher frequency waves would actually catch up to the lower frequency waves. And it doesn't happen. They stay the same distance away from those lower frequency crests. So the velocity of the wave is independent of f and lambda. In fact, the only way you can change the velocity of a mechanical wave is to change the medium itself. And to do that on this simulation, we'd have to change the tension. And we can see right away, when I drop the tension a notch, now the waves are slower. Again, the effect of frequency and wavelength is inversely related to each other, but the only way I can change the actual speed of the wave is to change the medium's tension.
Okay, that was maybe a little more, than you wanted to know, but I like the visual of it. I loved it that he saw that you could see with your eyes that when you doubled it, it halved it, right? So I think that's pretty cool.
I also noticed that the little green dots
Uh-huh.
didn't move.
Oh, really? Okay. And I think that's what he was saying. He was saying that really,
They stayed there,
the
but
velocity's
they
not
moved
changing
down.
because the velocity of the sound, speed of sound is the same if you're in the same medium. In other words, it's not going to go any faster than 775 miles per hour. Unless it's really, really hot. And then go a little faster. Or really, really
Technically-
cold, go a little slower.
The greenhouse, if there was something else, would actually be moving, right?
I don't know if those are supposed to just represent the energy, maybe. And remember, the energy moves, but yeah. So it's energy moving through the medium. All right. So energy's moving through it, but it's like on a wave of water. The water's not really moving, just the energy is. It's weird. Okay, so we're going to talk about these different sounds and what can we hear. Frequencies above 20,000 hertz are called ultrasonic waves. I'll have a better picture here in a second. Ultrasound. Frequencies below 20 have infrasonic waves. We can't hear below that. So our low to high pitch is in the range right here between 20 hertz and 20,000 hertz. Okay, so hearing ranges of various species. So humans, here we are between 20 and 20,000. That right there, yeah. Dogs can hear lower sounds and higher sounds. We know that whole thing about a dog whistle, right? How they blow the whistle and we can't hear it, and supposedly dogs can. All the dogs come running. Look at dolphins. Wow. So dolphins and dogs are about the same there. Fish can't hear really, really higher frequencies. Sea lions are less than humans, but go a little higher. Bats, we know about bats. I think we're going to watch some on bats here in a second.
Oh, higher.
Frogs, boy, howdy, they don't have very good hearing. They don't have very good range of hearing. Birds, that's surprising. And rodents. Have you ever seen those little things to help get mice out of your house, and it's supposed to be a high-pitched sound that we can't hear? So there's something to it. There may be something, because they can hear that. If it really bothers them, they'll go away, right? And we can't hear it.
We
All right.
can't hear, but does it damage our ears?
No, it doesn't, because it doesn't vibrate our cochlea at all.
Oh, it's just like
Doesn't even register. They're around us now. We don't even can't even hear it. Okay, so we're going to do a hearing test. Now, some of my younger students, students who I've had for many years, you'll recognize this one, okay? And this is where you're going to listen and maybe even close your eyes, or maybe not close your eyes, but just listen closely, and when the sound comes, put your hand up and tell me. And you remember where it was on the scale. Oops, I had to do it. Here we go. That's not it. And also at the very beginning it goes click, and that's
Hello,
not it.
would you like to try a hearing test for high-pitched sounds? Please make sure that you carry out the test under quiet conditions,
Okay.
without any background noise, and of course, don't forget to use enclosed headphones.
Yeah, sorry.
Pause the video as soon as you start hearing a high-pitched sound in order to see your results.
You'll have to remember your results.
Starting in 5, 4, 3, 2, 1.
Not that. I'm way after y'all. What were y'all at?
Whoa.
Like
I
around
was at
15 or 16.
Now it's just starting to hurt your ears a little bit.
16.
Grandmas.
Oh,
This
I
is
ran
grandma.
through the.
I know, I did better than Grandma. 90-year-old World War II artillery veteran. Go to the doctor right now. Deaf as a stone. Okay, so where were y'all?
60.
I think 150.
Oh, we gotta go back.
Yeah, we gotta try that again.
Okay,
That's
try
pretty
again. I feel very old. I'm gonna go on this side. Oh, I wish I had not recorded all this part of it. Blah, blah, blah.
Hello, would you like to try a hearing test for high-pitched sounds? Please make sure that you carry out the test under quiet conditions, without any background noise, and of course, don't forget to use enclosed headphones. Pause the video as soon as you start hearing a high-pitched sound in order to see your results.
I can do that.
Starting in 5,
I'm
4,
gonna,
3, 2, 1.
not that. I got some hands up right there
I
at
got
Yeah, around
120.
15.
right about
Mine was
120. So that says excellent and remarkable. Nobody was bat, dog, superhuman, unbelievable, or
I
amazing.
was.
Where were you?
Yeah, I was at like the bat and dog.
You are not.
Yeah, totally. I was totally at the bat and dog.
Okay, we're going to keep going to see where I am. I'm better than Grandma, I know that. Right there. So I had very good. I'm at 100, very good. Did anybody not have 120? I didn't see if all y'all raised your hands.
Oh, I did one.
I can hear it. I can hear it.
Yeah, I had
Sure,
120.
but-
Okay.
I can hear it's loud.
I'm just going to move ahead then. Are we good to move ahead then? Okay.
Because I can kind of hear.
So the pitch of the sound, the pitch, remember between high and low pitch, is affected by the frequency. Depending on the wave frequency, we hear either a high or low sound. High frequency, high pitch, we've already said this. Low frequency, low pitch. Okay, so frequency of the wave. See, there's lots more waves here than there are here. Okay, which brings us to the Doppler effect, which is a frequency disturbance. Okay, because something's moving, you see how this car is going into its own sound? It's not going to go faster than the speed of sound, so it's not going to have a sonic boom, but it is going to warp the sound a little bit. So the Doppler effect is a change in the sound frequency caused by the motion of the sound source and the motion of the listener, or both. Okay, so here we go. We have this, you've all noticed this, when you hear a siren going by, and it starts and it sounds one way and it passes you up and it sounds different, then it sounds different again. Okay, so it's kind of like, it kind of warps it, right? Well, that has to do with this thing known as the Doppler effect. All right,
Can't
so.
sirens hurt your ears?
Well, especially if you're real close to them.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right, yeah, so we'll get into that red shift about planets and stars moving away from us and how they're all moving away from us. Not just moving away from us.
Maybe they're scared of you.
Big Bang started somewhere real close to us. How about that?
Well, it could be because since we're orbiting it seems that like everything else is orbiting.
But something should be moving with us, right? Alongside us.
No.
So they shouldn't have red shift.
Maybe the aliens are afraid of
And there's nothing moving toward us.
Is the moon?
The moon is it's not emitting light, so we can't see that. So it's only reflecting light. All right, so ultrasound is a medical breakthrough. Sonar is useful in marine environments, war technology, etc. Ultrasonic radar aids in air traffic safety. That's like that beep, going beep, one of those things. Infrasonic geological mapping. Are y'all supposed to write these things down?
Yes.
Okay.
We are.
Sound technology, useful applications. Yeah, echolocation in animals, echoes in canyons. Okay. Well, I don't know how technological that is, but in animals, I think it's probably technological because it helps them to do something better, catch their food, whatever. All right. So, but in other words, we're taking sound waves and how they act and how they're very predictable, and we are using those in ways that help us. We'll get into some details of some of those here in a second.
I love
Actually, I don't know. Wait, are we supposed to hear this down?
Are you? What does it say?
Yeah, we are.
Yes.
Writing some of them down. So ultrasound sonar, ultrasonic radar. I'm not sure the infrasonic geological mapping is sort of like when we use waves of earthquakes to tell us what things are made of inside the earth. That's how we know it. That's how we have good guesses about what the center of the earth might be made of, the core.
hot lava.
Yeah. The deeper down, is it solid or liquid? All right, I'm gonna keep going. All right, so here's our ultrasound up here. So we remember here, we can't hear it, but shrews, insects, dolphins, and bats can, and dogs too, right? They're not up there right now. We're in the yellow part. The
Like
yellow
dogs-
part is humans.
Dogs are in the they're all the way at the bottom.
Where are the dogs?
Like right above the yellow.
Oh, right here. That is not consistent with the other chart that we had. Huh, weird. It shows dogs right here.
And elephants.
We have ocean waves, volcanic activity. These kind of things are all down here. Look, a blue whale can hear sound all the way down here. Elephants have a pretty good range, it looks like. Severe weather, interesting. Okay,
dogs,
so
should be higher.
dogs
They
should be
can-
higher and a little bit lower according to our other chart. So I'm going to question that one. All right, so ultrasound wave technology is called sonography. Do you have a blank for that? This might be from my old presentation. But y'all see what's happening here. You see the little baby?
Little baby.
It's a baby. There's a head and the nose and the mouth and the chin and a little hand, little leg, right there. So we can see the baby without surgically going into a womb, right? We can look at it with sound waves. I will say that some people say that the babies can hear it, or at least they're disturbed by it a little
Don't the
bit.
sound waves hurt them?
Sometimes they move. I don't know if they're in pain. I don't know. Let's watch this little thing and see if it helps us.
Yeah.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Okay, there we go. So I want you to look at this picture right here.
Oh, it's
This-
one of the new sonograms.
This is one of the newer sonogram types that has a, like what they call 4D, which brings time into it, right? And you can see, so you see this little, this is my granddaughter.
What is 4D?
It brings in time.
How does it bring in time in a photo?
Well, when they take it, it was live when they were taking it. Okay, so the baby was with it. So this is my little Elizabeth. You see her little nose, her mouth, her foot, right there. And so they sent me this picture before she was born. We didn't know it was a girl yet, but we're looking at it. They did this thing to make sure all the parts were there, right? So I'm looking at her saying, where are her eyes? Well, I don't see any eyes. She's going to be born without eyes. No, her eyes are fine. In fact, here's what she looks like. Oh my goodness. Is that adorable or what? She's fixing to turn 4, and she's a brat. Did you hear that, Elizabeth? You're a brat. Okay, an example in nature of using sonar to find food and navigate is bats and dolphins and whales. We can see they send a sound out through their blowhole, through the melon in their head, and they can bounce it off something they know how big it is and how far away it is.
I do that.
Bats do this as well. I think we have time to watch this bat video. And maybe we'll skip the dolphin video.
Have you ever heard someone say they're blind as a bat? Well, that expression is a bit misguided. During the day, some kinds of bats can see almost as well as humans, but when the sun goes down, nocturnal bats rely on their ears more than their eyes to navigate. This special navigation process is called echolocation. In echolocation, bats use a combination of their voice, ears, and echoes to create a perceptual map that allows them to see in the dark. You might be wondering where an echo comes from. An echo is the reflection of sound reaching a listener. Sound is a vibration that ripples away from its source in waves. The rate at which this vibration occurs is called its frequency. Sound waves at high frequencies are high-pitched. Humans can hear sounds at frequencies between 20 and 20,000 waves per second and don't perceive pitches outside that range. Bats, on the other hand, can hear and produce sound at frequencies over 100,000 waves per second, way beyond the range of human hearing. Here, we've slowed down a bat's chirp so you can hear it. This chirp is the first step in the process of bat echolocation, the primary sound that the bat will use to detect information about its surroundings. The bat listens as the chirp leaves its body and bounces off its surroundings. When the sound returns to the bat, the cartilage of the outer ear funnels the sound waves into the ear canal. The waves then reach the eardrum, which vibrates in response. These vibrations are transferred further into the ear to the basilar membrane, which runs the length of the cochlea. If you uncoil the cochlea and the basilar membrane, they would look like this. Each area of the membrane moves in response to a particular frequency. Then, the cochlea converts these vibrations into nerve impulses for the brain to interpret. The bat echolocates so fast that it can track down a dinner of insects moving around in complete darkness. Special muscles in its throat make it possible for the bat to chirp 160 to 190 times per second. Because it receives so much information at once, it has to differentiate relevant information from signal clutter. To do this, the bat emits chirps of varying frequency patterns, each of which echoes off objects differently depending on the object's size, shape, and distance from the bat. Then, by analyzing resulting echo intensities, it creates a mental map of its surrounding physical space. When looking for prey, the bat first sends out low-frequency chirps over a wide range. Larger objects will reflect more intense echoes, but it's often the smaller objects, like insects, that the bat is targeting. Once a bat receives low-intensity echoes from small potential prey, it will re-emit a high-frequency chirp directed toward it. When both high and low-frequency echoes return to the bat, it is able to ignore the now irrelevant low-frequency waves that reflect from the trees or rocks that surround its meal. To gauge how far away a given object is, the bat analyzes the time delay between when it hears its chirp and perceives the resulting echo. Directional information comes from comparing information the bat receives in each ear. For example, let's imagine that a bat's chirp echoes back from an insect to this side of the bat. Since this ear is closer to the insect, it will receive the sound before the other ear. By interpreting the difference between when it receives the echo in each ear, the bat can guide itself towards the insect. Bats are only one type of animal that uses echolocation. Killer whales, dolphins, porpoises, and some birds echolocate as well. Scientists who developed sonar and radar got their ideas from the study of echolocation in bats and whales. The U.S. Navy and other research groups are especially interested in echolocation because it could lead to even more technology. Maybe now you'll think twice the next time someone says, blind as a bat.
All right, so dolphins do it too, but they make a sound here, and it amplifies through that thing on their head called the melon. See right here, the melon, so it originates here in their blowhole. That's where their sounds come from, not their mouth. And it goes through and sends it out this way, and then whatever it hits comes back and it resonates through their jaw. Remember when we put the tuning fork and touched it with our teeth, how it went through there so well? That sound comes through that bone of the lower jaw of the dolphin and helps to locate stuff. So we're going to skip that video about the dolphins so we can get to our lab. All right, we're going to be doing this standing wave tube thing over here, and that takes sometimes a little bit of time. So let's get to that.